Chapter 5 is a fairly short chapter here in Stat 210. We're talking about continuous random variables, and we're by no means covering all the continuous random variables in this first chapter. We're actually just covering one distribution, and it's a distribution that's going to kind of help us get a good grasp on what's going on with continuous random variables. And then from there, we'll kind of start discussing more distributions in the next few chapters. So chapter 5, we're talking about continuous random variables. And in this chapter, we're going to learn how to recognize and understand continuous probability distributions. We'll also learn how to find probabilities of events within a continuous distribution. And this chapter really just introduces us to continuous random variables in a manageable way. And the remainder of the semester will be spent largely using continuous random variables as we discuss inferential statistics. So before we get into our distribution that we're going to spend our time on today, we're going to go ahead and talk about some properties of continuous random variables that all the different distributions that are continuous are going to share in common. So first, the graph of a continuous probability distribution is a line or a curve. And the probability is always represented by the area under the curve. So this is going to be some sort of line or curve that's above the x-axis. And the probability is the area between that line and the x-axis. The curve is called a probability density function, or PDF, and we use lowercase f of x to represent the PDF. So we're going to have some function for a line or a curve. So f of x equals some equation, and that gives us that line. Now, f of x does not give us, little f of x does not give us the probability or the area. The area under the curve is given by a different function. And if you know anything about calculus, you'll kind of understand the relationship here a little bit. And if you're going on to take calculus, this is kind of interesting to pay attention to. But the area under the curve is given by a different function, which we call capital F of x. And big F of x is called the cumulative distribution function. So for those of you who have taken or will take calculus, little f of x is the derivative of big F of x, or you could say that big F of x is the integral of little f of x. Okay, so some more properties. The outcomes for a continuous distribution are measured instead of being counted, and that's something that we know from when we originally defined discrete and continuous when we were talking about data way back at the beginning of the semester. The entire area underneath the curve but above the x-axis is always equal to 1, and that should make sense because probabilities should always add up to 1 if we have all of the different outcomes that are possible in our sample space. And now a unique thing here for our continuous random variables is that probability is found for intervals of x rather than for individual values of x. And we're going to kind of explore this a little bit more as we continue on this chapter. But really what this shows us then is the probability that c is less than x is less than d is the probability that random variable x is in the interval between c and d. And it's equal to the area underneath the curve between c and d. Now, the probability that x equals c is actually equal to 0. And because of that, we would say that the probability that c is less than x is less than d is the same as the probability that c is less than or equal to x is less than or equal to d. Now, kind of thinking about that a little bit, I'm going to draw a bit of a picture here. So here we have our x-axis. In black, and I'm going to draw it in blue and give you some sort of curve there and finding a probability. Here's C, here's D, all of this area in here. That would be the probability of being between C and D. So that there, or that there, or really this as well. Now, why can we not find, or or it's equal to 0 when we're saying the probability equal to C? Well, just equal to C, that is just this purple line here, which if you're colorblind, that's probably not helping too much. So let's just draw that in black. There we go. Now, thinking about finding the area, we would need to know the height of that line and the width of the line. But a line has no width, it just has a length. So we wouldn't be able to find area. Therefore, the probability is equal to 0. All right, let's keep talking. Finding the area or the probability. So to find the probability by hand, you need to be able to find the area, which finding the area is not too bad as long as you have a nice pretty shape that you know. In the picture that I drew on the last slide, that shape would not be one that we would know because it's some curve on one edge and then 3 straight lines on your other edges. And that would not be a shape that we readily know the formula for. And when I'm saying readily know the formula for, I'm talking like in elementary school, middle school, junior high, high school, you learned in geometry class formulas for finding area of certain shapes. So you're thinking like circle, triangle, square, trapezoid, parallelogram, rectangle. Those are pretty much, your shapes that you found areas for commonly. Maybe you worked with pentagons or other polygons, but oftentimes, you were fairly limited with what you had a formula for of area equals, and you had to memorize the formula and be able to use that. So most of our continuous random variables that we're going to look at, you're actually not going to have some nice pretty shape that you're going to know the formula for, which is kind of unfortunate for students that don't know calculus, because then you're a little bit stuck. If you know calculus, you're always going to know what that f of x, that curve that was drawn, that line that was drawn, you're always going to know that formula. So if you know calculus, you could just use calculus to find the area underneath it. But we don't know calculus for this class. You don't have to know calculus. So what are we going to do? Well, since we don't have calculus, we would use tables or calculator functions for most of our distributions. But there is one distribution that you do not have to have calculus for in order to find the area or the probability by hand. And so we're going to work with that distribution in this chapter so that we kind of have an idea of what's going on, a little bit of a grasp, so that as we start expanding this to distributions where we don't have the ability to find it by hand and we're having to rely on tables and calculators, that we can do it without a ton of issue, and we kind of have a grasp or an understanding of what's going on. So the uniform distribution. So we're going to use the uniform distribution to kind of help us all get a grasp or understanding of what's going on. The graph of the uniform distribution is a straight horizontal line, and this allows us to form a rectangle between the line and the x-axis. Now, if we have a rectangle, we should know the area of a rectangle. Area of a rectangle is length times width. Thus, we can use this to find probabilities. So the uniform distribution assumes the random variable can assume any value between a and b with equal probability. So some formulas, f of x equals 1 over b minus a. That gives us our line that we're drawing. Our probability that we're between a value c and d then is equal to that line times the distance between c and d. Our average is a plus b added, so a and b added together and then divide by 2. And then your standard deviation is the square root of b minus a quantity squared, all divided by 12. So let's say the time that it takes to wash dishes is uniformly distributed between 8 and 15 minutes. So to draw this, we would say, okay, f of x equals 1 over 15 minus 8, which is 1 over 7. So we could draw a pretty little line there, and that shaded it in the area should have an area of 1. And we could take a look at it. We would say, okay, this length here, that is 7. My height is 1/7. 7 times 1/7 equals 1. That means we have the right line drawn. Now for this distribution, instead of having what is technically called the line, we have what is technically called a line segment. So there's a starting point and a stopping point for it. All right, so what if I wanted to find the probability that it takes between 10 and 11 minutes to wash dishes? Using that same distribution that we have, well, we have our picture. Now, if we're saying between 10 and 11 minutes, we have that shaded in area, that darkly shaded in area. So we could use our formula. We'd find it's 1/7. Or we could say area of a rectangle. What's the height? What's that width? And we get 1/7. Now we could also find the mean and the standard deviation. Using our formula for mean, we'd be taking 8 plus 15 and dividing by 2. So we get 11.5. Standard deviation, using our formula, we have 15 minus 8, square that, then divide it by 12, then take the square root. So we have 2.02. And that's it. That's chapter 5. Fairly short and sweet, but that kind of gets your toes wet a little bit with continuous distributions.